chapter, not only you can have like counter flow liquid extraction, you can also have cross flow extraction. Okay, like this. So for the cross flow extraction, you're gonna have multiple lines of operating lines. Okay, so what each stage has its own operating line, like this. Okay, so different lines may have different slope if the ratio of R to E is not equal. Okay, if the ratio of R to E is not equal, then the slope of each operating line can be different. Okay. Yeah, this is the graph for the cross flow. And again, like for these techniques, we kind of assume that the system is kind of dilute, right? When it's dilute, then the raffinate flow and the extract flow, they kind of constant. When you assume that you have dilute solute in your system, then R and E doesn't change. Okay. But if your if in your system if you have like high concentrated of solute, then you cannot say that R and E constant. You have to, instead of using R and E, you have to use FD and FS instead. Okay. So like assume that the flow of diluent and flow of solvent kind of constant, but R and E not constant because there's a transfer of the solute from one liquid to another. So R and E are not constant, but we still assume that FD and FS constant. Okay, for concentrated system. Okay, and this one right here probably still one of the most difficult to understand. I don't know, you guys, have you guys like review how to draw the triangular diagram? Hello, anyone still with me? Anyone has any question about the triangular diagram? You guys know how to draw the lines, like find the tie lines, conjugate lines, solubility envelope, everything? Any questions? Questions? Okay. Thank you for responding. Seriously, like but okay, but let me recap again then. Yeah, I suggest you to. Oh, okay. Anyway, yeah. But if you I hope you guys already watched this YouTube clip on how to draw the ternary diagram. But okay. But anyway, so let me recap this. Yeah, so you have like counter current system like this, right? But this counter current is the actual process, right? But you can like make imaginary process, you know, like from this diagram to hold on. Okay, yeah, from this diagram to this diagram, okay, from like the actual process to this imaginary process. So in the actual process, you have like multiple stages, right? Multiple stages, and the flows like flow counter each other. But from this, you can redraw the diagram into this imaginary process. It's like you have a stream of solvent, E, and stream of feed Rn plus 1 goes into this kind of mixture, and then combine them together becomes flow M. and this phloem goes into some kind of black box that separate in outlet into En and R and R1. Okay, so this process right here is like imaginary process. Okay, but from this you can like draw this diagram like if you draw the intersections line, you know, like the line between the line ENR1 and the line SF, they intersect with each other at the point M. Okay, like this point M doesn't exist in real life. It's like imaginary. It's an imaginary point. Okay, it happens when you draw the lines and they intersect with each other. Okay, and then from this you can derive these mass balances and equations here to find the coordinate M. Okay, this coordinate M can be used to find many things. Okay, like for example, maybe maybe the problem gives you AS, information about AS and information about AF and R1, but the problem doesn't give you En. Okay, the problem doesn't give you En. So you can use this equation here. Okay, these equations here to solve for M. Okay, to solve for M. Once you know M, then you can just draw the line, you know, from R1 pass through point M, and then you will get En on the other side. Okay, so that's one of the useful thing about point M. Okay, to use it to find some information that we don't have at the beginning. Okay, and in addition to point M, there's another imaginary point. It's called the delta point. Okay, this delta point is right here. Okay, so this delta point is imaginary point is out of the diagram. Okay, it's out of the diagram, but it can be useful in finding the number of stages. Okay, this delta point can be useful to finding the number of stages. By example here, okay, in this example, you find delta, right, and then you start from R1, and then you find the tie line to this one. So this is E1 right here. Okay, this point is E1, and then you can draw the line from delta point to E1 and pass to the other side to this point, so you get R2 here, and then from R2 you can find E2, and then use the delta point again, draw the line to R3. Okay, to R3, and then R3 to E3. Yeah, and you keep doing it until you get E4, E5 here, and finally you gonna get E6 here, but this E6 is above En, so the number of stages should be a little bit less than 6. Okay, so that's how you use delta point. Okay, you use delta point and ternary diagram, the triangle diagram to find the number of stages. Okay, so this is one technique. And another technique is to use the combination between the triangular diagram and the McCabe field diagram. Okay, like this. Okay, so this is the equilibrium, and this is the operating line, and this operating line comes from the information from the operating line comes from the information of the triangle diagram. Okay, and with this you don't need to use conjugate line. Okay, so like in this technique, okay, in this technique you need to use tie lines and conjugate lines to find the number of stages. Okay, this is the conjugate line. Okay, this line right here is conjugate line. You have to use conjugate line and tie line to help you find the number of stages. But with this technique, you don't have to use conjugate line. Okay, you just need to find the delta point. Okay, and like try to draw several random lines, straight lines to find the overlapping lines. And once you get the overlapping line and equilibrium line, then you can find, use the usual procedure, draw the steps to find the number of stages. Okay. Yeah. So let me again show you my work. Okay, so for the first problem, it's just liquid extraction. Okay, so I have the equilibrium line. I draw the overlapping line and find the number of stages. Okay, so this is a simple liquid extraction. And the next one is the cross flow. Okay, so this problem cross flow, I think your friends use they did not use the graphical technique. They just use mass balances like stage by stage calculation. That's fine too. Should give you the same result. But with the graph, it's kind of it also like kind of give you some insight when you draw the graph. Okay, so this one is for the cross flow system. And then the third problem, this one is the one with partially immiscible system. So this one you have to use the triangular diagram. So first I use this technique here. You make use of the tie line and the conjugate lines like this. Okay, and I also use another technique with a combination of the triangular diagram and the Mackay field diagram, and got about the same answer, 1.7 and 1.8. Okay, so you can use either technique. Okay, no question really. Okay. Then I move on to the last chapter. Actually, the last chapter is very simple. Probably it's kind of like totally different from other process that we learned so far. It's the filtration. Okay, and the filtration that we focus on is the one with the cake, traditional filtration. When you run the filtration system over time, you're gonna get the accumulation of solid, which is called cake, on the surface, on top of the filter. So the cake itself will act as additional filter. Okay, and the cake getting accumulated over time, getting bigger and bigger. Yeah. So basically, this is the final equation that you use for this system. So it's a combination of two resistances: the resistance to the filter and the resistance due to the cake. Okay, and from this equation, you can use it in two modes of operation of filtration. Okay, the first mode of operation is when you use constant pressure drop. Okay, when you try to maintain the pressure drop inside the system, and doing this is gonna change the flow rate. Okay, when you try to maintain the pressure drop, the flow rate is gonna change, and you can rearrange the equation into this form right here. and when you do some experiment, when you get some experimental data of volume, collected filtrate volume over time, you can make a plot of TV versus V, and you can find the slope and intercept. And these slope and intercept can be used to determine alpha and Rm, which give you the information about the resistance of the cake and the filter. So basically, you can do the experiments and to determine the nature, to learn about the properties of the cake and the filter. Okay, to find the resistance of the cake and the filter. And another mode of operation is going to be constant rate. So this time you don't control the pressure drop, but you control the flow rate instead. By trying to keep the flow rate constant, then the pressure drop is not going to be constant. It's going to change over time. So you just rearrange the equation and get into this form instead, and then you can do the experiment delta P versus V. Like measure delta P over time, volume over time, and then make a plot of delta P versus V, and then you can find the slope and intercept, and this slope and intercept also can be used to find alpha and Rm, which tell you about the resistance of the cake and the filter. Okay, and the exercise simple. Make a plot, find slope, give you slope and intercept, and slope and intercept can use to calculate alpha and Rm. So this chapter is kind of it's
เขาให้ฝนหาปะเขาให้ฝนหาปะ
Okay. And the exercise is pretty much the same. In this exercise, like first problem, like the filtration works at constant rate, constant flow rate. But then in second problem, they switch mode from constant flow rate to constant pressure drop. But the cake, the material of the cake and the material of the filter is still the same. So alpha and Rm is still the same because it's the properties of the materials. So we can use the same value of alpha and Rm in the second problem calculation. Okay, so that's pretty much everything I want to say. I don't know, you guys have any specific question? Or maybe it's still too soon? Like you guys maybe gonna ask me again like 1 or 2 days before the exam or something, or I don't know. Any question right now? No?